Okay, in the last video, we took the Laplace transform of e to the at, a function of t, and we got 1 over s minus a function of s, with the restriction that s had to be bigger than a. Okay. Anytime we learn what a Laplace transform is, we learn the corresponding inverse Laplace transform. Remember, we said the Laplace transform was 1 to 1, which means it's invertible. So if I have this function of s and I apply the inverse Laplace transform, it will give me this function of t. And of course, with the understanding that here s is bigger than a. Okay. Should probably go ahead and write that in. Okay. Now, I want to just take a moment and address what you are and are not responsible for memorizing. You're not responsible for memorizing this formula. I have here a very handy-dandy handout, which you can find on the class website under handouts, okay? It's a table of frequently used Laplace transformations and some rules for Laplace transformations. It's actually just tables 6.1 and 6.2 from your textbook, but I would encourage you, rather than just referencing that in the text, to actually print this out and have it with you as you're doing homework, as you're doing quizzes, and as you're doing exams. Yes, you will have one on the exam. I will provide it for you, however, because I reserve the right to leave one of the formulas off. So you don't need to have that memorized, but I could ask you to derive it. So if I'm asking you to derive it on an exam, I might not include it on this nifty table. Now, it might be that I do include it on the table and I ask you to derive it. All that means is that you'll know what your answer is supposed to be and you can just confirm, but all of your points that you'd be getting for that problem would be in demonstrating that that's the correct answer. Okay. So you're never responsible for memorizing the Laplace transform. You should know the definition because, of course, if I asked you to derive this, you would have to apply the definition of the Laplace transform to evaluate that improper integral. The way the table works is like this. Rather than writing two separate equations, the Laplace transform of this is that, the inverse Laplace transform of that is this, it just has two columns where it says, here's my function of t, which I can view as the inverse Laplace transform of the function of s, and here's the function of s, which I can view as the Laplace transform of y. And it gives you the function of t and then the corresponding function of s. So going this way, we're applying the Laplace transform, and going this way, we'd be applying the inverse Laplace transform. What I've added to the handout that's not in the textbook is that number 1. This is Formula 1, okay? On quizzes and exams, when you're using a Laplace transform, if you use any of these rules, you're going to say by Formula 1, or by Formula 5, or by Formula 77. There are not 77 formulas, so we don't really need to worry about that. Okay. But you can reference it that way. And these numbers aren't included in the textbook. They're just my way of making it easy for you to explain your work. If you're doing things right, it ought to be clear to me what formula you're trying to use. If you're doing things wrong, it's not always clear. So this just sort of covers your bases and mine that we're communicating about what you're trying to do. Okay, so 6.1 gives me these Laplace transforms for various functions. This is the first one, and we'll slowly be working through. There are actually 10 of them. We'll be working through the Laplace transform for all 10 of those functions of t as we work through this chapter. Table 6.2 gives us some rules for Laplace transforms, and I'm going to give us just a few of those right now. Okay, so let's let f of t and g of t be functions defined on the interval from 0 to infinity with no more than exponential growth. Okay. So in other words, we can take the Laplace transform of f and g. Okay. The Laplace transform of f of t plus g of t is the Laplace transform of f of t plus the Laplace transform of g of t. So the Laplace transform essentially distributes over addition. Okay. And then if, let's see, what do I use for my constant in the rules here? Alpha. Okay. If alpha is a real number, it doesn't really matter what I call it, but this is what it's called on the formula sheet. Okay. The Laplace transform of alpha times f of t is alpha times the Laplace transform of f of t. Okay. These two properties, for those of you familiar with the terminology, basically say, that the Laplace transform is linear. Okay. It preserves addition, it preserves scalar multiplication. In other words, you can add and then take the Laplace transform, or you can take the Laplace transform and then add, you get the same thing. You can scale by alpha and then take the Laplace transform. You can take the Laplace transform and then scale by alpha. You get the same thing. Okay. Putting these rules together, if I allowed alpha to be -1, I could, and combined it with this addition rule, the Laplace transform also preserves subtraction, because it would preserve f plus -1 times g of t, which is just f minus g of t. Okay. Important fact, since L is linear, the Laplace transform is linear, so is the inverse. Okay. That's always going to be true. If I have something with these two properties and it's invertible, these properties will be inherited by the inverse function. Okay. Now, the other property that I want to go over right now of the Laplace transform is that it is invertible. Okay. Now, I've stated that. I'm going to just state it again, but I want to talk about an interesting sort of technicality there. Okay. So the Laplace transform is 1-to-1 and thus invertible. I'm not going to prove that, but hopefully that seems reasonable to you. Because the Laplace transform of y of t is the improper integral from 0 to infinity of y of t times e to the negative st dt, it seems kind of unlikely that having two different functions here could lead to the same thing in terms of s. Turns out that's not possible. Okay. So hopefully that seems reasonable to you, but I'm not going to do a formal proof. But what I do want to point out is that while we say it's invertible, okay, remember that Laplace transforms were only defined for functions defined from 0 to infinity. So if this is my t-axis, and I have some function here, where this is f of t from 0 going off towards infinity, okay? For the purposes of Laplace transforms, this function, which is just constant until we hit 0 and then behaves like f of t, is the same as this function, which would be constant at 0 until we hit 0 and then jumps up to here, is the same as this function, which kind of curves down to this point and then continues on, because the Laplace transform only considers the behavior from 0 to infinity. Okay. So, for the purposes of Laplace transforms, the three functions that I've drawn that have three different beginnings, but the same ending from 0 to infinity, would be basically considered the same function. So when if I were to apply the Laplace transform to this, and then apply the inverse Laplace transform, it's going to give me this back, going from 0 to infinity, but the inverse Laplace transform doesn't tell me anything about what happens for negative values. So if I wanted to have the inverse Laplace transform give me a unique function defined on everything from negative infinity to infinity, I could define mu naught of t times f of t. Mu naught of t is just this nifty function. It's kind of an on switch. It's 1 if t is bigger than or equal to 0, and it's 0 everywhere else. So it's basically saying, turn the function on at time 0. The function is off, so that would give me this function here. It's off. It's at a value of 0 until we hit time 0, and then it starts behaving like f. So if we wanted to do that to extend the domain of our functions to go from negative infinity to infinity, but still have a unique function that would be the inverse Laplace transform of something, we can certainly do that. Okay. So just sort of an interesting technicality, because functions like e to the at, obviously I know that those are defined for negative values of t, but the Laplace transform is treating that as just a function from 0 to infinity. So when I apply the inverse Laplace transform, I'm going to get a function from 0 to infinity, and it's always going to agree there, but there could be multiple functions that have different behavior to the left of that. If I want to get a unique one, this is sort of the standard way to do it. So say, hey, all functions are defined to be turned off for negative values of t. We turn them on when t is equal to 0.